Okay, so welcome back. So we are just about to construct our subsequence of this original sequence x, which is going to converge on our lim sup, which we're denoting L. So we start off with our interval L minus 1 to L plus 1, and I want to find an element of this sequence that is within L minus 1 to L plus 1. I want to prove that there exists such an element. Right, okay, so the first thing to note is that L is the limit as n approaches infinity of this sequence Sn. So Sn is a monotonically decreasing sequence. So this is L, and you've got the terms of this sequence, let's say S1, S2, and they converge down on L basically. So that's what's happening. That's what L is. Okay, so if this sequence converges to L, then that means that for all epsilon greater than 0, there exists a point, a big N, in this sequence, so a big N which is an element of the natural numbers, such that if little n is greater than or equal to big N, it implies that, let's say, that S little n is an element of the interval, the epsilon interval around the point L. So basically what I'm saying is give me any epsilon interval, L minus epsilon to L plus epsilon, so this is the interval L minus epsilon to L plus epsilon. I can find you, by the definition of convergence here, I can find you a point, a big N, in this sequence, so an S big N, so let's say S big N, such that all that term and all terms after it, so all little n that are greater than or equal to big N, all of that term and all terms after it are going to be within this interval, basically. So basically what I can do is I can find you a point in the sequence, so the sequence starts off with S1, S2, S3, etc. I can find you a point, S big N, such that that term and all terms after it are within this epsilon interval around L. Okay, so just set epsilon equal to 1. If this converges to L, and if we're given that it converges to L, then that implies this, so that epsilon equal 1, and I can find you some S big N such that all of those terms after that term and all other terms after it are within the interval L minus 1 to L plus 1. Okay, so what that means is, if I draw another picture, here is L, here is my interval, this is L plus 1, this is L minus 1, I can find you some S big N such that that term and all the terms after it are within this interval, basically. Okay, so now let's just use that Sn, and remember what the definition of Sn is. Sn is equal to the supremum of the set containing all terms of the original sequence x from the nth term onwards. So this is the supremum of this great big set. Now, but if this is going to be a supremum, what does it mean? It means that it's, one, an upper bound for this, and secondly, that any term that's that's less than Sn, so any number that's smaller than Sn, cannot be an upper bound, i.e. there must exist a point in here which is within this set that is strictly bigger than any number less than Sn. So if I take, for instance, Sn minus epsilon, so some point, let's say, let me get a different coloured pen to make it more obvious. So let's take some point down here, which is Sn minus epsilon here, okay, then that cannot be the supremum of this set, basically, which means that there must exist some point in this set. Let me get another colour as well. Spent quite a bit of money on these different coloured pens for these videos, so I might as well use them. So there must exist some point in this set which is within this, which is in here, basically. There must exist some point there. Right, okay, so you might be able to guess what I'm going to do now. I'm going to say let this epsilon equal 1, basically, and then what we've got is Sn minus 1. So if we draw the interval Sn minus 1, here is Sn here, so basically that interval is going to look something like that, because it's going to be this is Sn minus 1 here. So if we look at this sort of interval between this point and the Sn, then that is going to have the same length as the distance from L to L minus 1 here. The point is that because Sn is to the right of L, then Sn minus 1 is also to the right of L minus 1. So this interval from Sn minus 1 to Sn is completely contained within the interval L minus 1 to L plus 1, basically, is the important thing. Right, now, just by this definition here, there must exist some point in this set which is between Sn minus 1 and Sn. The reason being that if there weren't, it would contradict Sn being the supremum, because the definition of Sn being the supremum says that for any element less than Sn, and Sn minus 1 is certainly less than Sn, there must exist some point in this set which is strictly greater than that. So, take whatever that point is. There is a point in here, take it basically. So let's say it was xn plus 1 here. That point was somewhere in between here. Just take that point. There must exist some point. Find that point, and basically that is going to be the first term of my subsequence which I'm trying to construct, which is going to converge. Okay, so, right, so let me get some more paper, or is this, no, it's not clean on the other side. Right, okay, so, this is going to be our first term, basically. This is going to be our first term in the subsequence, our first term in the subsequence that I'm trying to construct that is going to be convergent, basically. Okay, so let me call that, we don't know what term it is, it's just any abstract term in this set, xn onwards, basically. We don't know which one it is, you just had to find one, basically, and all we know is that one exists, otherwise it will contradict Sn being the supremum. Okay, so let's call that term, let's call that term, whatever its name is, we'll call it xi1, and the reason I'm calling it xi1 is it is the term that was in the first interval, the interval of radius 1, so this interval L minus 1 to L plus 1, so it was the interval corresponding to, if we go back up here, it was the interval corresponding to a little n is equal to 1, so that's why I'm calling it xi1. I don't know what i1 is, it's some natural number greater than or equal to big N, but we don't know what it is. All I've shown you is that there is some element of the original sequence x, so I'll redraw out the original sequence x, x1, x2, x3, etc. There is some element in this original sequence x which is within the interval L minus 1 to L plus 1 here, basically. And that element that we found is xi1, basically. Okay, so now what we need to do is construct our second point in the sequence. So now what we're going to do is we're going to look at the interval, and we're going to look at the second interval now. So we're going to go to look at the interval L minus a half to L plus a half. Okay, and we're going to try and find a point in the sequence x, which is within this interval L minus a half to L plus a half, but we've got a new condition now, which is that the term we want has to be beyond xi1, basically. Okay, so how are we going to make sure, because remember the definition of a subsequence was you pick some elements, so the first element we've chosen is xi1. xi1 is somewhere along this sequence, so let's say it's over here. Okay, now we're picking the second element of our subsequence, and basically it has to be to the right of xi1. We do not want it to be over here somewhere. So that we've got another precaution that we have to take now, another condition we have to try and satisfy. Okay, another hoop we have to jump through. Okay, right, so apart from that, the argument is the same. I'll just show you where to modify the argument, basically. So the argument is that because the limit as n approaches infinity of Sn is equal to L, that there must exist a point, let's call it S big M, not to confuse it with S big N. In fact, should we call it S big N2, because we're now working on the second interval, and we could then call this big N here. We could have called this S big N1, basically, to denote that it's the one for the first interval. So now what we're doing is we're saying, okay, let epsilon equal half, because this sequence of this S sequence converges to L, there must exist a point in the S sequence S where that term and all terms following it are within this interval L minus a half to L plus a half. So call that point, that term, that first term, Sn2, to denote that this is the n for the second interval, basically. So we've got S big N2, and again, this, remember, by definition, is the supremum of all the terms of the original sequence from xn2, xn2 plus 1, xn2 plus 2, etc. And note that the 2 is subscripting the n. The plus 1 is sort of on the level of the n. The 2 is a subscript there, so don't let that confuse you. I'm not putting 2 plus 1 in the subscript. I'm putting n2 plus 1, basically. Okay, right. Now is the point where the alteration has to happen, because at the moment we're all poised to then say, okay, now because Sn2 is the supremum of this, we can construct another interval. We can say take Sn2 minus 1 there, and then I can find you a point of this set here that must be in there. So again, I found you a point that has to be within this interval L minus a half to L plus a half, so will that be our second term? The problem is, how am I sure that that term, the next term, the xi2 as we're going to call it, how am I sure that that is to the right of xi1? So this is the point where we need to make an alteration. So we need to... Basically, the way we found this Sn2 so far is we said, okay, here is the sequence S, so I'll draw that out, S1, S2, S3, and then you go on all the way up to Sn2, and basically, from that point, Sn2 onwards, all of those terms of the sequence were within this interval L minus a half to L plus a half. That's how we've found Sn2 so far. What we're now going to say is, I want you to take this into consideration, but I also want you to make sure that N2, let's say, in fact, I'll continue on the way I was going to say it. We also want to make sure that N2 is not just big enough that it's, it's the starting point of where all the terms are within this interval. We want to make sure that N2 is beyond whatever I1 is. So I want N2 to be greater than I1 as well. The reason I want it to be greater than I1 is because if it's greater than I1, then all of these terms here in this set, the set for which it's the supremum of, is going to be a set of terms of the original sequence that are all beyond xi1. So basically, if this point here, this n2, is greater than whatever this number I1 is, so let's imagine I1 was the 1,000,000th term of this sequence, then if n2 is greater than 1,000,000, then that means that the set over which we are taking the supremum of is, let's say n2 is 2,000,000, it's going to be the set x2,000,000, x2,000,000 plus 1, x2,000,000 plus 2, and all of those terms are going to be beyond this term in the sequence. So when we then do this argument of saying, okay, go to Sn2 minus 1 and find me a point in this set that is within there, or whatever point you choose, it will necessarily be beyond x1. So when we choose that point as the next term of this sequence, it will be in the right order, i.e. it will be after xi1 in this sequence. So that is our second condition. I'm saying, okay, find me the point after which all of these terms are within, find me the points in this sequence S after which all the terms are within this interval L minus a half to L plus a half, but also I want N2 to be greater than I1. So, if this point, the original choice for N2, in fact, should we make a new N2? Should we make N2 prime? And I'm going to define N2 prime to be the maximum of N2 and I1, basically. So, what I'm actually going to do is, instead of looking at Sn2, I'm going to look at Sn2 prime, basically. So N2 is the point in the sequence S after which all of these points are within the sequence. So get rid of this, basically. So with the motivation that we want to take the point in the sequence after which not only is it in here, but also it's greater than I1, I'm going to define N2 prime, basically. I'm going to define it by this, because N2 is the point after which all the terms of this sequence are within this interval L minus a half to L plus a half. I1 is the term of this sequence here. In fact, actually, we might have a problem there, so let me just add on 1 to that. Then it's safe, because basically what we're trying to do, remember, is we are trying to find some number. Sn2, remember, will be the supremum of the set xn2 prime, xn2 prime plus 1, etc. We want the terms of this set that we are taking to be after xi1. So that's why we are taking the maximum of i1. Okay. We also want the terms of this we want to look at the point. We want Sn2 prime to be a point within this interval L minus a half to L plus a half. As long as n2 prime is greater than or equal to n2, it will be true that it is within this interval. So we do not need to choose n2 specifically. We can use any number after it. So I'm basically saying let n2 prime be some number potentially after n2, which has the property that it's bigger than i1. And that's what this is saying here. So if I1 happens to be greater than N2, this maximum will be I1, and then you'll add 1 to it, and because I1, so N2 prime will end up as I1 plus 1 if I1 is greater than N2. If N2 is greater than I1, then we've got no problem. But the problem occurs if N2 isn't greater than I1, which is why we're defining this and rectifying that problem. So, if N2 is smaller than I1, then you'll go to I1 plus 1, which will be a set of, all these terms here will now be beyond I1, because you'll start off at xi1 plus 1, xi1 plus 2, etc. So they will all be beyond xi1, but it will also have the property that they are all within this interval L minus a half to L plus a half, because we are beyond N2 basically. I1 plus 1 is greater than N2, so we are beyond this point in the sequence. We're somewhere over here, which means we are definitely within that interval L minus a half to L plus a half. Okay, so I hope I have communicated the necessity for doing that. Okay, so now we've got this this set here, which Sn2 prime is the supremum of. We pull exactly the same trick. We say, okay, here is L, here is Sn2 prime, and here is the interval L minus a half to L plus a half. What we then do is we say, okay, take the point Sn2 prime minus 1, minus a half you'd want to do now. That is still going to be completely contained within this interval, because Sn2 prime is to the right of L, so it's bigger than L. Therefore, when you take a half away from it, that is still going to be greater than L minus a half. So basically, because Sn2 prime is greater than L, when you subtract a half off both sides, it will still be true. So this is going to be completely contained within this interval, basically. Okay, so now what we do is we just apply the definition of the supremum. This is the Sn2 prime is the supremum of this entire set here. So that means that if I take any number less than it, which Sn2 prime minus a half certainly is, then there must exist some point in this set which is basically in between them there. Take that point. And let that be the second point of our subsequence. So we then have xi1, xi, and this new point, this red point here, that's going to be xi2. So we've now got the second point of our subsequence, and basically xi2 is now assured to be beyond xi1 when you view them as being terms of the original sequence x. So here is the original sequence x, x1, x2, x3. You go along, somewhere along is the term xi1, and basically we are assured that xi2 is beyond there, basically. The reason being that n2 prime, all of the terms of this sequence are all of the terms of this set that you're taking the supremum of. So all of the possibilities for xi2 are n2 prime, xn2 prime plus 1, etc. And n2 prime is bigger than I1. Because I've defined it so carefully, I assure you that n2 prime is greater than I1. So that's why we were doing this, so that we can assure that this second term that we choose for this subsequence is beyond the first term. And then you continue on. So you go then to the interval, you go to the third interval, you go to L minus a third, to L plus a third, etc. You then find a point in the sequence S, so you find some Sn3, which is definitely within this, which is within this interval L minus a third to L plus a third, and all terms beyond that in the S sequence are within that interval, which you can do because Sn converges. So then we have Sn3 plus 2, etc. All of those terms of the S sequence, so here's S1, S2, S3, they are all contained within here. And then basically what you choose, again, you choose an n3 prime, which is going to be the maximum, in this case, of n3 and now I2, and then you'll add 1 to that. So basically this takes account of the fact that if n3 is smaller than I2, then we risk the fact that when we do this supremum trick again, we could end up picking a term of the x sequence which is to the left, i.e. before xi2 in this original sequence x. So to circumvent that, to get around that, we say, okay, if you have this catastrophe that I2 is greater than n3, we'll just go beyond it, because the definition of limit means that all of the terms after it are also within there, so they're all good to use as well. So basically just go along to one that is bigger than I2, bigger than I2 plus 1 specifically, and then we'll be done. Obviously if n3 is greater than I2 alone, you have no problem basically. Okay, and you continue that on, and in that way you will build up a subsequence of this original sequence x. So you build up xi1, xi2, xi3, xi4, and you just continue constructing like this, and all of these terms will be in order with respect to the order in which they appear in this sequence here. So basically you just continue on the process that I've described to you already, and you get a subsequence of x. Now all that's left to prove is that this subsequence converges to the limit L. Okay, and that's pretty easy because of the way that we set it up with these intervals, these intervals that are getting gradually smaller, i.e. L minus 1 over n to L plus 1 over n. Right, so if we want to prove that this sequence xi1, xi2, xi3, etc. is actually converging to the limit L, so we want to prove that it converges to the limit L, then what we need to prove is that for any epsilon you give me, I can construct you an interval L minus epsilon to L plus epsilon. I don't know why I've labelled those. That should be L minus epsilon, that should be L plus epsilon. So I can construct you an interval L minus epsilon to L plus epsilon, and I need to be able to find you a point in this sequence, some x I big N now, such that that term and all terms beyond it are contained within this interval L minus epsilon to L plus epsilon. So let's say let epsilon be greater than 0. So take an arbitrary epsilon. What I need to show you is that I can construct a point after which I can find you a big N basically, for which that term and all terms in the sequence following it are contained within this interval. Well, what's beautiful about this is that if you take the xi little n term, what we know is that that is contained within the interval L minus 1 over n to L plus 1 over n. We also know, that's just by definition, that's how we were finding these points. We were finding points of the original sequence x, which were in the interval L minus 1 over n to L plus 1 over n. So this first term was in the interval L minus 1 over 1 to L plus 1 over 1. The second interval was in the interval, the second term was in the interval L minus 1 over 2 to L plus 1 over 2. This one was in the interval L minus 1 over 3 to L plus 1 over 3, etc. So we know that the nth term is within the interval L minus 1 over n to L plus 1 over n. Okay, we also know that xi n plus 1 is going to be an element of L minus 1 over n plus 1 to L plus 1 over n plus 1. But those intervals, this new interval, this is L minus 1 over n plus 1, and this is L plus 1 over n plus 1. So this interval, this next interval, is contained within the previous one, the L minus 1 over n to L plus 1 over n. So this is contained within there, which means that xi n plus 1 is an element of L minus 1 over n to L plus 1 over n. So basically, xin and all terms in this sequence beyond there are elements of this interval L minus 1 over n to L plus 1 over n, just by induction of what we've done here. So how can I write that? Let's say for all little n is greater than or equal to big N, xi little n is an element of L minus 1 over big N to L plus 1 over big N. So if I let big N just equal some arbitrary natural number, so let's say that big N is equal to some arbitrary natural number, then if you take any term in this sequence up here that is beyond, or well, is equal to big N or beyond big N, then that has to be contained within the interval L minus 1 over N to L plus 1 over N, because it's going to be greater than or equal to that, so it itself will be contained in some interval, let's say L minus 1 over little n to L plus 1 over little n, and that interval is basically going to be much, much smaller than the interval L. So this is L here, this small interval here is the interval L minus 1 over little n to L plus 1 over little n, and this one here is the big interval, because of the fact that little n is greater than or equal to big N. Okay, clear? Right, so now it's easy basically. All we have to do is make this interval contained within the interval L minus epsilon to L plus epsilon. So basically, if I find you some xi big N, which is within this sequence, then all which is contained within this interval L minus epsilon to L plus epsilon, well, if I make this interval here contained within L minus epsilon to L plus epsilon, then it will be true that all of these terms here from big N onwards will also be contained in there. And that's easy. All I have to do is make 1 over big N less than epsilon. So here's a picture. Here is L. Here is our interval L minus epsilon to L plus epsilon. Okay, and all I have to do is basically make the interval L minus 1 over big N to L plus 1 over big N contained within there, and then what we know is that the term xi at big N will be in there, and all terms following it, all the terms xi little n that are bigger than or equal to big N will also be contained within that interval L minus 1 over big N to L plus 1 over big N, which implies that they will be contained within the interval L minus epsilon to L plus epsilon. So all I need to do is make 1 over big N less than epsilon, and that's the equivalent statement that N is greater than 1 over epsilon. So basically, if you give me an epsilon, all I have to do is take its reciprocal, which I can do because epsilon is not equal to 0, so its multiplicative inverse exists, and then I need the first natural number. So if this is 1 over epsilon, just go to any old natural number, big N, which is greater than that real number. So let's say you get some hideous real number like 11.99, then you could go to 1112 as your next natural number that would be bigger than that. And basically, if you look at all the terms of this sequence beyond xi 1112, then they will be within this interval L minus epsilon, whatever epsilon was, to give you 119, a multiplicative inverse of 111.99. Okay, so that's the proof basically that this sequence does indeed converge to L. So what I've done is I've constructed you, in theory at least, in principle at least, you could actually do this for any bounded sequence X. What I've shown you is that it's possible to construct it's always possible to construct a sequence which converges to the lim sup of any bounded sequence. So that is the Bolzano-Weierstrass theorem proven.